So let's think about voltage dividers. So a very simple voltage divider would be as it is shown here. You have two resistors and a voltage source attached to them. And one of the resistors is variable. So I've called the variable resistor R and the fixed resistance RF. And you could take the voltage either from across RF, or the output could also be taken across R. Okay, what is the output voltage going to be? It's a fairly basic thing. The output is given by this equation. Okay, and therefore we can see that the voltage output is a function of the variable resistor, and therefore the change in resistance is going to be converted into a change in voltage. Now, how does that work in terms of a potentiometer? So in a potentiometer, as we have already seen, one of the resistors is 1 minus alpha RT, where RT is the total resistance of the potentiometer, and the other resistance is alpha into RT. Now, of course, this alpha is a function of X, which is distance of the wiper from one end of the potentiometer. And if you do some maths, it's fairly straightforward, and I'll leave you to work it out. You can see that you can get X, which is the displacement of the wiper from one end of the potentiometer, as a function of the output voltage. Therefore, if you measure the output voltage, you can get the displacement of the potentiometer. Okay, so next, let's just take a look at one example where we put a sensor in a voltage divider and how it works out. Okay, so what we're going to do is we're going to use, instead of a variable resistor, we just use a thermistor there and see what that means. So here's a circuit where there's a thermistor in place of a variable resistor, and we know the how the resistance changes as a function of the temperature for a thermistor. Okay, so what is the output of this thermistor? The output is given by VO, which is equal to V RF over RF plus RT, right? And now what we can do is, instead of RT, we can substitute the resistance of a thermistor with respect to time, and what we get is the equation like this. Okay, and this can be further simplified in the following way. And what I have done in this case is I have written this exponential function of temperature as a function f of t. Okay, and now we can simplify it a little further by doing this. We can say this is equal to V is 1 over 1 plus S f of t. Okay, and you could write this entire function, which is here, as V capital F of t. Now there's a reason why I'm doing that. This actually helps us to choose and use thermistors, and that is what I'm trying to explain in this particular slide. If I plot this f of t versus the temperature, okay, for different values of S, remember what S is? Essentially, S is given by S is R0 over RF. So R0 is the base temperature of base resistance of the thermistor, and RF is the fixed resistance and the voltage divider. And if we have that, what we can do is we can plot Ft over T for different values of S. And we notice that for this material, if S is 1.5, let's say, if S is 1.5, we have an almost linear response of the thermistor from around, let's say, from around a little above 0 degrees to somewhere around 20 degrees or 40 degrees. Yeah. So if we want to use our thermistor between, let's say, around 10 degrees to 40 degrees, we could choose an S of 1.5. But instead, if we want to use our thermistor between let's say 80 and 100 degrees, probably a S of 20 would be better, because at that moment we'll have a more linear relationship between the output and the temperature. So that's the advantage of writing the equation like that. Well, having done this, what I want to next focus on is talk about amplifiers for voltage dividers. So here's a voltage divider, and I want you to think about an assumption that we make in this voltage divider. The assumption that we make as we write equations for the voltage divider is that whatever current flows through the variable resistor also flows through the fixed resistor. So this I is the same as this I, right? So that means that what we are assuming is that there is no current drawn out of the voltage divider through the output terminal. So I naught is essentially equal to 0. And if that assumption is not met, the output of the voltage divider changes. So if we connect an amplifier to our voltage divider so that we can amplify our signal, we need to make sure that this I amplifier, the input current to the amplifier, is 0. Now, is it possible to have an amplifier where the input current is 0? Of course, no, it's not. So you will never have an amplifier where the input current is 0, but probably the current is so small that you can actually neglect it. Before we think of ways in which we can actually choose amplifiers that make this current small, let's just think about the effect of a current being drawn on the circuit. So one of the ways in which you can capture this effect of a current drawn from the voltage divider is by using a resistance RL in parallel with RF. And you can see that if you're trying to measure R, the effect essentially is that RF gets replaced by RF parallel RL, which means that if RL is infinite, that is, if no current is drawn, then the output is very close to the ideal one. As RL starts becoming smaller and smaller, your resistance that you're measuring starts to get distorted, and you don't get the right values. Okay, coming back to the amplifier, we said that what we want is that the amplifier current is 0. Now, what kind of amplifier topology do you have where you can have the amplifier current as 0? Of course, if you have a background in a little bit of op-amps, you know that one of the topologies is a non-inverting amplifier. So in this case, the current I bias is almost equal to 0. In an ideal op-amp, if you take an ideal op-amp assumption, this current is actually 0. But in real life, it's not going to be 0. It's going to be a small current, but probably small enough so that you can ignore it. As an exercise, it would be interesting to figure out how the output voltage changes as a function of the bias current.